Across the observable universe, galaxies rarely float alone. They are threaded along enormous invisible filaments known as the cosmic web. These structures stretch for hundreds of millions of light years, guiding where matter gathers. Gravity alone cannot explain their stability. Something unseen provides extra mass, shaping the skeleton of the universe. Astronomers discovered galaxies forming chains and walls, not random scatterings. This pattern hinted that a hidden framework existed long before the first stars ignited. The key to this hidden framework is dark matter. It does not emit, absorb, or reflect light, yet its gravitational pull dominates cosmic architecture. Without it, galaxies would spin apart because visible stars lack enough mass to stay bound. Observations of galaxy rotation revealed outer stars moving too fast to remain stable. Instead of escaping, they orbit smoothly, implying a massive halo surrounding every galaxy. Dark matter halos act like enormous containers holding galaxies together. When astronomers map galaxy clusters, they see giant bridges connecting them. These bridges are not made of gas clouds or stars but invisible mass concentrations. Computer simulations show that early density fluctuations after the Big Bang stretched into long strands as gravity amplified them. Ordinary matter then flowed into these channels, like rivers following valleys. Galaxies formed where filaments intersected, producing crowded nodes known as clusters, the busiest regions in the universe. Between the filaments lie enormous cosmic voids, regions almost empty of galaxies. These voids help confirm the web's existence because their shapes match theoretical dark matter patterns. Matter was pulled away from these spaces and gathered into surrounding walls. Over billions of years, the voids expanded while filaments thickened. The universe became more structured rather than chaotic. The pattern resembles soap bubbles or neural networks, revealing surprising order on unimaginable scales. Between the filaments lie enormous cosmic voids, regions almost empty of galaxies. These voids help confirm the web's existence because their shapes match theoretical dark matter patterns. Matter was pulled away from these spaces and gathered into surrounding walls. Over billions of years, the voids expanded while filaments thickened. The universe became more structured rather than chaotic. The pattern resembles soap bubbles or neural networks, revealing surprising order on unimaginable scales. Gravitational lensing provides direct evidence of the hidden scaffolding. Light from distant galaxies bends while passing massive regions. By measuring distortions, scientists map invisible mass distribution. The resulting maps outline filaments even where no stars exist. It is like seeing footprints without the creature. These measurements prove that most of the universe's mass lies outside luminous galaxies. The visible cosmos is merely decoration hung upon a much larger invisible framework. Gas flows along filaments toward galaxies, fueling star formation. Without this supply, galaxies would run out of material quickly. Cold streams of hydrogen travel for millions of light years before settling into galactic disks. This process explains how galaxies kept forming stars for billions of years instead of dying young. The cosmic web therefore acts not only as a skeleton but also as a transport network, delivering raw material across intergalactic distances. Galaxy clusters sit at filament intersections where gravity is strongest. Here thousands of galaxies orbit within vast dark matter wells. Hot plasma fills the space between them, glowing in X-rays. The temperature reaches tens of millions of degrees, showing how violently matter fell inward. Yet even this massive gas accounts for only a fraction of total mass. Most of the cluster's weight remains invisible, reinforcing the idea that dark matter dominates cosmic structure. Simulations of the early universe start with tiny fluctuations in density. As time progresses, these fluctuations stretch into a web remarkably similar to telescope observations. This agreement suggests the universe evolved predictably from simple beginnings. Slight variations after the Big Bang determine where every galaxy would later form. Our own galaxy exists because ancient ripples guided matter toward one specific filament billions of years ago. Supermassive black holes also follow the web's architecture. Galaxies feeding them receive constant inflow from filaments, allowing the black holes to grow enormous. Active galactic nuclei shine brightest in dense regions connected by multiple strands. Even cosmic radiation patterns align with filament directions. The universe behaves less like scattered islands and more like a living network exchanging matter and energy across unimaginable scales. Researchers use radio telescopes to detect faint hydrogen between galaxies. These signals trace filaments directly, confirming theoretical predictions. The gas is extremely thin, far emptier than any vacuum created on Earth, yet spread over immense distances. Observing it required decades of technological advancement. Each detection strengthens the picture of a universe woven together rather than randomly populated with galaxies. Dark matter particles remain unknown, but their behavior is clear. They interact primarily through gravity, passing through ordinary matter almost untouched. This allows halos to overlap and merge smoothly during galaxy collisions. When clusters collide, luminous gas slows from friction while dark matter continues ahead. The separation proves they are different substances. Such events provide rare laboratories to study the universe's dominant but invisible component. The Milky Way itself sits inside a vast halo extending far beyond its visible stars. Neighboring dwarf galaxies orbit within this gravitational envelope. Streams of torn stars mark past mergers guided by the same hidden structure. Even our night sky owes its stability to the dark framework surrounding us. Without it, the galaxy would have dispersed long before planets could form. Over time, filaments evolve slowly as gravity continues shaping them. Clusters grow larger while smaller groups merge into bigger structures. Eventually, most galaxies will drift toward massive nodes, leaving voids emptier than today. The future universe will appear darker and more isolated, yet its underlying web will remain intact, stretching across distances too vast for light to cross again. Understanding this structure helps explain cosmic expansion as well. Dark energy pushes space outward, but dark matter anchors local regions together. Galaxies within the same filament remain bound despite overall expansion. The balance between these forces determines the universe's long-term fate. Observing how filaments stretch over time allows scientists to measure the strength of cosmic acceleration. The cosmic web also influences where life could emerge. Dense regions create heavy elements through repeated star formation and explosions. These elements travel along filaments into new galaxies, seeding planets with necessary chemistry. Our solar system contains atoms forged in distant clusters connected by ancient structures. In a sense, life depends on the universe's hidden architecture. The more we observe, the clearer it becomes that galaxies are not isolated objects but features of a grand design. Invisible matter outlines corridors across the cosmos, guiding motion, growth, and evolution. Stars, planets, and even observers exist because of the silent framework. The universe is not empty space with scattered lights. It is a colossal network, and we reside on one small strand of its endless web.